Welcome back everyone. So in this lecture actually I will continue to do more problems. So like I said, it will help you to actually get a very good grip on what we have done so far. So now in this lecture I will actually do some problems related to sl2 representation theory. So let's begin. So we actually proved complete reducibility for all finite dimensional representation of sl2c, and as well as we classified all irreducible representations of sl2c. Okay, so what we observed while proving that, okay, if we have a finite dimensional sl2 representation, okay, and in which if we have a w inside w which is a non-zero element, such that this w is an eigenvector, h eigenvector, and let us say x also kills this w. Okay. So, x kills w and this h acts as some scalar. So, let us say that scalar is d. Okay. So, this is for some d in let us say z plus. So, then if you recall the proof that we have done, that actually tells us that, so the subspace spanned by the following elements, okay, the subspace spanned by the following elements w, y dot w, etc., y power d w. So, this is exactly equal to the submodule generated by this vector w, okay, sl2c submodule. Not only that, if you call this is some capital W, this capital W will be isomorphic to V of t. So, this is actually hidden in the proof of what we have done. So, one way to actually again you can go through the proof and then see that this subspace which we called it W is actually invariant under the action of x. Okay, that is the only thing we need to prove. So, I will just outline, I am not going to go through again entire proof. So, the way we proved I will just outline. So, you take this W to be the span of these vectors W, y w, etc., y power d dot w. Okay. So, now what one can prove? One can prove that this subspace is actually indeed submodule for this capital V. Okay. So, first step 1. So, try to prove W is invariant under sl2c action. So, it is clear that it is H invariant, because W is being H eigenvector. You can see that y w will be actually d minus 2 will have d minus 2 eigenvalue and so on. So, if you calculate the H action on this y w, you can prove that this is d minus 2 times y w, okay, and so on. So, that tells us that these w, y w, they are all eigenvectors for the operator H with the eigenvalue corresponding to d, d minus 2 and so on minus t. Okay. These are all the H eigenvalues. So, these are all H eigenvectors. So, now if you go back to the calculations that we did using the formulas that I wrote down, because this x is actually killing w and then this h is acting as dw. So, then you will be able to prove these 2 implies y power d plus 1 w is 0. Okay. So, once you convince that y power d plus 1 is w is 0. So, then it is clear that this span of w, y, w and so on, that is invariant under action of y, because this y will just increase the powers, but y power d plus 1 w is 0. So, you are still inside this subspace w. Now, if you take x and then again if you use this formula that we have actually wrote down for x times y power k, then you can see that using the same computation that we did earlier, this thing will be invariant under again the action of x. So, that makes w is invariant under sl2c action. So, now using that same calculation, you can see that this basis w etcetera y power dw, because they corresponds to distinct eigenvalues of this operator h. Okay. So, that means they are all linearly independent. So, that implies that this these vectors will form a basis. So, in particularly we can explicitly compute the action of sl2c on each element of this basis. So, that will coincide with whatever you have seen for this irreducible model VD. Okay. So, compute explicitly the action of x, y and h on this basis w, y w etcetera y power dw, and see it coincides with the calculation that we have for V of t. Okay. So, that makes that this is actually irreducible. So, for example, the same proof that we did it for V of d works here as well, because if w is not irreducible, then it should have proper non-zero submodule. But if you start with any proper non-zero submodule, so call it w dash. Okay. So, then this will have h eigenvector. Okay, because it will have h eigenvalue, because h will map w dash to w dash, h is being diagnosable will imply that h restricted to w dash is also diagnosable. So, that makes there is an eigenvector inside this w dash. For example, some y power I w will be inside w dash, but now from this using repeated application of x and y on this y power I w, we get all other elements in this w, y w etcetera y power dw. So, that proves that this w dash must be equal to w. So, that actually kind of gives us contradiction, that proves that w must be irreducible representation, which is isomorphic to V of t. Okay. So, this is actually very important observation, that if you are able to pick some w which is maximal in the sense that x is killing w and it is an eigenvector for the action of h whose eigenvalue is also like integer. Okay. So, not integer, just non-negative integer, then you can guarantee that this submodule generated by or the subspace generated by these vectors will be isomorphic to irreducible representation V of t. So, this is a very important observation. So, this will be used throughout in the structure theory of semi-simple Lie algebras. So, one should get comfortable with this observation. So, now I am going to actually tell you how one can actually deal with any given finite dimensional representation of sl2c. So, for that maybe I will actually recall or not recall, I will just try to prove some of the facts about this finite dimensional representation of SL2C. And then using those facts, you can see that you can get more comfortable with the finite dimensional representation theory of SL2. So, for that, to begin with, we start with the finite dimensional representation of SL2C. So, then using complete reducibility, we know that, so this is also called Weyl's theorem, okay, because Weyl proved the complete reducibility in general. So, we will call this as also Weyl's theorem. So, using Weyl's theorem, so which is same as complete reducibility. Complete reducibility for this finite dimensional representations, okay, of more generally semi-simple Lie algebras, but anyway here for SL2C we can also restrict. So, this V can be written as direct sum of irreducible representation. Of course, some of the VI's can be isomorphic. Okay. So, these VI's are all irreducible finite dimensional representations of SL2C. So, now we can actually see that using this we can immediately get all the eigenvalues of H. When it acts on capital V, so that should be all integers, okay. All the eigenvalues are integers. Why? Because this we know it for all irreducible finite dimensional representations of SL2C. So, using a complete reducibility we get this for free for capital V. So, not only that, so if we take this H restricted to this kernel X, okay, so which will map kernel X to kernel X. So, then so these maximal vectors that generate this individual V1 etc. Vk, all of them lie inside kernel X, and that will actually form a basis for this kernel X. Okay. That is something we have seen in the proof of complete reducibility. So, kernel X, let us say span by this V1 etc. Vk. So, where these Vi's are coming from this capital Vi, where X is killing and H is acting as this Ni Vi. Okay. Because it is again kind of diagnosable on kernel X. So, you can take it to be H eigenvectors. So, that is what we observe. But anyway, we will see later there is another way to actually decompose V into direct sum of irreducibles using some other method. So, that method is more efficient than looking at the kernel X and so on. So, now what is important? Important is all the eigenvalues of this H acting on V, they are all actually integers, that is most important thing. So, now we can also conclude something about so number of components that appear in this capital V. Okay. This K is the number of irreducible components. Okay. So, let us say this K. So, this is the number of irreducible components occur in capital V. So, one can wonder whether this K is unique or not with respect to capital V. So, of course, we are going to conclude this K has some formula. So, that formula also tells us that this is actually unique, okay. But there are other ways to actually convince ourselves this K must be unique. So, what is that formula? So, you can easily see that this K has to be dimension of this V naught plus V 1. Okay. So, what is that? So, this let me call it V, okay, maybe I will use this V 0 like this. So, this is those vectors in capital V where this H is actually killing, and then V 1. So, those vectors in capital V such that H V leaves V. So, that means one is the kernel of H, the another one is kernel of H minus identity. So, that means V naught corresponds to the eigenspace of with respect to H of eigenvalue 0, and then V 1 corresponds to eigenspace corresponding to eigenvalue 1. Okay. So, now it is easy to see this k will be just a dimension of this V naught plus dimension of V 1. Okay. So, why this is true? So, if you go back to your decomposition, so V is written as some V 1 direct sum etcetera V k. Now, this each V I will be of the form V of d I for some d I coming from z plus, okay, that is non-negative integer. But what are all the weights or what are all the H eigen values of this capital V I? So, the H eigen values of this capital V I, so they are nothing but d I minus 2 and so on, minus d I plus 2 and minus d I. Okay. So, every time it jumps 2, okay, down and goes up to minus d I. So, that means for any given non-negative integer, either this sequence d I 2 minus d I. So, this sequence will contain either 0 or 1. Okay. And since each of these eigen spaces corresponding to these eigen values, they are one dimensional inside this VDI. So, that says this V 0 intersection this V I, or which is same as V 0 intersection V of d I. So, that is at most one dimensional. Okay. The dimension of this space is at most one dimensional. Similarly, the dimension of V 0 intersection V I will be V 1 intersection V I, that will be again at most one dimensional. Okay. It will be exactly one dimensional when 0 occurs inside this V d I. Okay. So, for that d I must be even. So, you can see that dimension of V 0 intersection V d I is 1 if and only if this d I is even. Similarly, so this is exactly V 1 intersection V d I is 1 if and only if this d I must be odd. Okay. So, that proves that if you are interested in counting number of this V i's, so you need to count only the dimension of V naught and dimension of V 1. Okay. So, put together you get the number of irreducible components. So, since the right hand side dimension V naught plus dimension V 1, so that is independent of this irreducible decomposition that we have chosen. So, that proves that this k will be actually independent of the irreducible decomposition that we have chosen here. Okay. What I mean by that? Suppose V is isomorphic to some, let us say W 1 direct sum etcetera some W r, where W i's are again irreducible. So, then we must get k equal to r, because k is given to be dimension V 0 plus dimension V 1, okay, which is independent of the decomposition. So, this is indeed very important observation. In some sense, these observations actually help us to actually give help us to decompose given finite dimensional representation of SL2. Okay, let us see how one can do that. So, before that, it is actually good time to introduce what is called characters. Okay. Again we talk about here in SL2C what is called H characters. Okay. So, H characters. So, I do not know whether I will be able to actually do this character theory in general, but anyway let us do this for SL2 in the introductory course, not a problem. So, what is this H characters? So, you start with V, which is a finite dimensional representation of SL2. So, when V is irreducible, okay, for example, V is V of D, it is very clear that the action of H somewhat tells everything about V of D. Okay. You have a basis and then you have this maximal vector V naught inside V D. Okay. This is a span of V naught, V 1, etc. V D. So, it is a D plus 1 dimensional space where H V naught is given by D V naught. So, more or less this H V naught is given to be D V naught, that determines what happens this to the H action on other vectors, and more or less this H actions which determines this this representation completely. Okay. If you think about it, all we need is one needs to know what happens when you apply the H on this V naught, okay, where this x V naught should be 0. So, once you recover this D, then you recover this entire representation. Okay. So, that is why it is important to actually keep track of the action of H alone. Okay. So, that is actually somewhat helps us to recover the complete representation. So, let me make it very precise. So, once I define what is called characters, then it becomes very precise what I was trying to tell. So, let us take this V to be finite dimensional representation of SL2C. Now, using Weyl's theorem, you know that this V can be written as direct sum of Vk, where each Vi are irreducible. Okay. So, now if you take this H action, okay, H acts on V. So, since H acts on each Vi as diagnosable operator, so H acts on V as diagnosable operator, acts semi simply on V. Okay. H acts semi simply on capital V. So, in particularly this V can be written as direct sum of this V gammas, where gamma is coming from C. But since we just saw from earlier observation that all the eigenvalues of this H are actually integers. So, in particularly one can assume that these gammas, they are all coming from integers. Okay. There is no issue. But what is V gamma? V gamma is nothing but it is just a eigenspace corresponding to gamma. So, this is those vectors in capital V such that H V is given to be gamma V. Okay. So, now this can be more dimension more. Only in the irreducible representation the dimension of each eigenspace, okay, if it is non-zero it has to be 1. But in general V, we do not know what it is, but anyway that is fine. But what we can do, we can keep track of the dimension of this gamma, sorry V gamma, and what gamma that occur here. Okay. So, that allows us to define what is called this character. So, the character of course with respect to H, and if the H is understood, then we just leave it and then write it as character of V. Okay. So, the character of V is defined to be summation dimension of V gamma times x power gamma, okay, where gamma is coming from Z. So, a priori this is living inside Laurent polynomial ring, okay, over Z. So, Z bracket x plus or minus 1. Okay. You can also think this sitting inside this Laurent polynomial ring over complex numbers, there is no issue. Since V is finite dimensional, so this is actually finite sum. Okay. Only for finitely many gamma, the dimension of V gamma can be non-zero. So, now this is something very important data. Okay. So, one can prove that, okay, I will actually state it as a theorem, because this is very important observation, and this is actually happens even for any semi-simple Lie algebra, but anyway let us do it for SL2, no issue. So, what we want to say, let us say V and W, they are given to SL2 representations. Okay. So, then what I meant by this character actually determines the representation. So, V is isomorphic to W, okay, as SL2 representation if and only if the character of V must be same as character of W. So, basically these two Laurent polynomials, they are same. If they are same, then immediately we get that this V and W are isomorphic. So, this is somewhat some kind of combinatorial data, that is actually we are recording from the representation, but somehow this combinatorial data, okay, which actually completely controls the representation. So, that is why the characters are very important in the representation theory of semi-simple Lie algebras. So, this is very important observation, that whenever the characters are same, then we get that this V is isomorphic to W. So, let us see like how one proves this. So, basically what you prove that these characters of irreducible representations, they are linearly independent. Okay. So, because we talk about linearly independence, let me actually work over C. So, one can also talk about Z linearly independent, but anyway it is easier for us to just talk over C, not a problem. So, what I want to say, if I take the character of this VD and then look at over all this non-negative integer, then this set, this is actually linearly independent inside this Laurent polynomial ring. So, if we prove that this character of VD, this set is actually linearly independent inside this Laurent polynomial ring, then we immediately get that this character determines the representation. So, one way is obvious. So, the forward way, if V is isomorphic to W, then that would imply that this dimension of V gamma and the dimension of W gamma, they are all same for all gamma in Z. So, that proves that character V must be same as character W. But for the other way, you assume for time being this character VD is linearly independent. Now, using Weyl's theorem, what we know, V can be written as some VD1 direct sum etc. direct sum some VDR. Similarly, W also can be written as some VD1 dash direct sum etc. direct sum V some DS dash. Okay. Now, if the character of V is same as character of W and this character of V of D, they are all linearly independent, then what we get? We get exactly equal to character of V of D1 plus etc. plus character of V of DR equal to character of V of D1 dash plus etc. plus character of V of DS dash. Okay. So, this is simple fact. If you take direct sum of two representation, then the character will get added. Okay. So, this I will leave it as exercise. If V is V1 direct sum V2, then character of V is same as character of V1 plus character of V2. So, that is not that hard to prove. So, from this we can see that if these two things are equal and they are all linearly independent, that forces that, okay, so this R must be equal to S. Not only that, this multiset D1 etc. dr must be same as D1 dash etc. d S R dash. Okay, this is I am treating it as a multiset. Similarly, this is also multiset. So, that proves that these multisets are same and the number of components are same, that means these two are isomorphic. Okay. So, that proves V is isomorphic to W. So, this tells us that character determines the representation. So, let us see how one proves this character of VD. They are all linearly independent. So, let us look at character of VD and then make some important observations. So, VD, we know that this is spanned by some vectors V0, V1, etc. VD, okay, small vd. So, whose eigenvalues we already written down. This is d minus 2 up to minus d. So, in particularly what will happen to the character of VD? So, the character of VD is explicitly, so because all the eigenspaces are one dimensional, so you get x power d plus x power d minus 2 plus etc. plus x power minus d. So, if you just use this expansion for this 1 minus x power n divided by 1 minus x, you can see that this is exactly 1 plus x plus etc. plus x power n minus 1. Okay. One way to prove this, you just multiply on both sides and then see. For example, if you take 1 plus x plus etc. plus x power n minus 1 and then multiply with 1 minus x, then you get 1 plus x plus etc. plus x power n minus 1 minus x minus x square plus etc. plus minus x power n. Okay. So, then you cancel all these terms. So, then you end up only this 1 minus x power n. Okay. So, that proves this identity. Now, if you use this identity here, you can see that you can take out this x power minus d. So, if you take out this x power minus d, then you get this is x power 2d plus x power 2d minus 2, which is x power 2 into d minus 1 plus etc. plus 1. Okay, the second term may be x d plus 1 plus x power minus d. So, if you take out that minus d, then you get 1 plus x here. So, yeah. So, this is sorry, this is 2. So, you get x square here. X square plus 1. So, now using this simple calculation, you can see that character of VD is x power minus d times. So, this you can think like 1 plus y plus etc. y power d, which you can replace with this. So, then it is 1 minus x square d divided by 1 minus x square. Okay. So, if you put it inside, you can see that this is you can also switch the sign. So, x power d minus x power minus d divided by this is x square minus 1. Okay. Sorry, this is going to be okay 2d, sorry, x square 2d minus 1 here. So, let me redo it. So, the character of VD is equal to x power minus d 1 plus x square plus etc. plus x power 2d. So, that means you can put y equal to x square. So, this is same as x power minus d 1 plus y plus etc. y power d. So, which you can write it as 1 minus y power d plus 1 divided by 1 minus y. Okay, that is this formula says. So, into x power minus d. So, then if you just rewrite this is x power twice t plus 1 minus 1 divided by x square minus 1 into x power minus t. So, this is x power d plus 2 minus x power minus t divided by x square minus 1. I guess I'm doing something wrong. So, okay, I will leave it to you to think about it actually how to simplify this. It's not hard to simplify this, but what is important, so the simplified form actually looks better. Okay. But anyway, without simplifying, you can see that the character of Vd is nothing but x power d plus x power d minus 2 plus etc. plus x power minus d plus 2 plus x power minus d. Okay. So, now if you take some sum of these characters to be like equal to 0, okay, some linear combination of this, let us say some ai character of Vdi, the combination to be 1 to k is 0. So, now what you can do, you can pick D1 which is maximal among all the Di's. Okay. So, that means this D1 is greater than or equal to Di for all I. So, then you can look at this A1, the character of this Vd1 plus the rest. Okay. So, if some of them are actually going to be like equal, okay, then it will come with some multiplicity. So, if d1 is equal to some di, then you count it with multiplicity, then you get some ni di. So, that way what you do, you first actually assume that these di's are all distinct. Okay. So, otherwise you just add the corresponding terms, so that this coefficient is actually changes. Okay. So, once you assume all di's are distinct, then you can actually make sure that this d1 is greater than di for all I not equal to 1. Okay. So, in particularly, so some a1 v character of vd1 plus some rest of the term will be equal to 0. But note that this character of d1 has this x power d1 which has coefficient a1 plus the rest of the term. All these terms and the terms coming from this, all of them will have degree definitely less than this d1. Okay. The degree of this x power I in this entire terms, that will be definitely less than d1. So, that makes, if by comparing the coefficient of this highest term x power d term, you can see that this a1 must be 0. If a1 is 0, then using the same argument you can prove a2 0 and so on. Okay. So, that proves that this character of Vd must be linearly independent over complex number. So, this is just by comparing the degree, highest degree term x power d term inside this summation. Okay. By eliminating that, you can come down and so on. So, I will actually leave it to you to check. Okay, you can simplify this. I believe the simplified form should be something like this: x power d minus x power minus d divided by x minus x power minus 1. Okay. Maybe we can actually trace back and then see whether this is correct or not. X power d minus x power minus d divided by x minus x inverse. So, if you just take it out x power minus d, then you get x power minus d times x power 2d minus 1 divided by x square minus 1 and then here x minus 1. Okay, so that will add up xd plus 1 x power 2d minus 1 divided by x square minus 1. So, this is what we are supposed to get. Okay, so if you take it inside, you get x power d plus 1 minus x power minus d plus 1 divided by x square minus 1. Okay, so let's go back and then see whether we got something like that. And yeah, we made a mistake, I guess. So here x square minus 1 is correct. So that is what we are getting here. And then x power minus d plus 1 we should get. So one term is missing. So basically you take out x power minus d. Yeah, here maybe like we must have made some mistake. So this is up to d we are adding. So here we are getting x square d minus 1. Okay. So this is correct. Twice d plus 1 minus 1. If we take one x out, then we are d plus 1 minus x power minus d plus 1. Sorry, x inverse out and x square minus 1. Okay, so I will leave it to you to check. It's okay, not a problem. Okay, I will stop here and then we will continue with the lectures in the next class. Okay. So as I said, this Jordan Chevalier decomposition will be very, very important in order to develop further theory. So I have made one video on that. So I advise you to go through that before actually getting into the next lectures. Okay, I will stop here. Thanks.